Hi, in this video, we look at the part two of resource constrained system design. It's important to use very lightweight protocols for energy saving. In fact, we have many protocols which supports less energy consumption. One of them is called COAP. The other one is MQTT-SN. MQTT-SN stands for Sensor Network, so sensor nodes or sensor networks. And one important concept that we should be aware about is about duty cycling. Okay, so what do you mean by a duty cycling? So coming to duty cycling, we can set up the device in such a way that we can make the device to sleep most of the time and then wakes only to sense and transmit. For example, a soil sensor wakes only once per hour. So it wakes for 1 hour and then it goes to a sleep for the next hour. So this is the first hour and this is the second hour and so on. So in such a case, our system is kind of in a sleep for 1 hour, and it wakes up only on the next hour, and then it transmits the values in that particular hour. So duty cycling is important to keep our energy utilization to the minimum. We will see an example problem for in an IoT air quality monitoring device which operates in a periodic low power mode. So periodic low power mode here means sleep mode. Okay, and then the power consumptions are given below. It will be using a usually it will be having an active current of 30 milliamps during uh, low power functioning, or when it is sleeping. It consumes only 50 microamps, and the active time is only 4 seconds and the sleep time is 196 seconds. So here it means that it is going to be active for a very small time, and then it is going to be inactive for a long time, and then active for some time, and like that. So active for 4 seconds. So this is 4 seconds, and this is going to be inactive for 196 seconds, and in the next 4 seconds it will be awake, and so on. So given that we have a battery capacity of 2000 mAh, uh, what we want to calculate is the duty cycle and also the battery life in days. So how can we calculate this? So the duty cycle is going to be a ratio. Is going to give you how much percentage is this device on for a duration. So for example, here we have 4 milliseconds of on duration and 196 milliseconds of sleep duration. So the total duration is 200 seconds. We have the duty cycle is defined by the sleep, the active time divided by total time into 100. So here we know that active time is 4 seconds, total time is 200, and to take the percentage, we multiply with 100 and we get 2%. Now, the average current during the sleep mode is mentioned as 50 microamps, which is nothing but 0.05 milliamps. And then we have to find the average current. So to find the average current, we know we know this point zero five milliamps is during the is going to be during the sleep time. The sleep time is 196, and the active time is 4 seconds. And at that time, the current consumed is 30 milliamps. So 30 into 4 plus 0.05 into 196, and the total duration is 200 seconds. So when we do this calculation, we are going to get 120 plus 9.8 divided by 200. Okay, so So we are going to get something like 0.65 milliamps. Now, to calculate the battery life, so we know that the battery has a capacity of 2000 mAh. 2000 mAh. And so we can divide this milliamps, whatever that average current utilized, can be divided with this battery battery mAh, which will give you 2000 divided by 0.65, and that will give you the number of hours. So if you do 2000 by 0.65, you will get 3076 hours. So if you convert it into number of days, how can we convert it into number of days? Maybe 3076 divided by 24. So it gives you something around 128 days. Okay. So this particular air quality monitoring device can operate for 128 days with a battery of 2000 mAh. Now, suppose we have not enabled, as a homework, what you can do is, suppose we don't have any sleep enablement, okay, and then come up with the number of days it can be operated in this particular battery. That is, under no, I mean, if there is no sleep, if no sleep mode, what will be the battery life? So the duty cycle is going to be 100 percentage here instead of 2 percentage, and you have to work out the other details. Okay. Now, moving to energy efficiency in IoT, so we have seen that we can use lightweight protocols. We can have duty cycling, all this, which are all going to improve the energy efficiency. Now, why is energy efficiency important? Because most of the cases we are going to deploy the devices in remote locations, like maybe in a forest, bridge, or farms. So the replacement of battery is going to be very difficult. So we have to maintain the energy efficiency. So for doing that, we have different options. One of them is energy harvesting, and the other one is dynamic power management, and then we have to also look at low energy communication. All these will lead to long battery life. Now, when you talk about energy harvesting, it is about making use of solar panels to generate energy and save it. Another form of energy harvesting is the RF energy. So RF energy basically picks up the signals in the environment. For example, the mobile tower signals, okay, and mobile tower signals and other signals, and then convert them into a small energy and save it. Similarly, you have the piezoelectric. So it is going piezoelectric sensors or piezoelectric nodes can pick up the vibration, convert vibration into power and save it. And also the other option is the thermal energy. So where temperature is converted to an energy and stored. So we have all these options available. Out of this, we are very familiar with the solar energy. An example would be a solar powered weather monitoring station where you have a lot of sensors, and then all these are going to be powered by the solar power, or the battery is going to be recharged by the solar power, and so it will last long. And the second point here is about dynamic power management. So dynamic power management is going to reduce the CPU speed during low workload. So the idea here is to, again, to turn off the unused modules. For example, if we know that for a particular period we are not using Wi-Fi and GPS, we can switch it off for that duration. And whatever modules are being unused, we don't have to operate them in full power. We can make it sleep for that particular time and then wake up whenever it is required. A typical example is, for example, if there is if in the case of motion detection, so I want to detect a motion, so I have kept a PIR sensor somewhere here. And if some motion is detected, for example, a human being is nearing to the PIR sensor, so at that time I want to enable my camera and my Wi-Fi and my GPS to send the image across a network, and also the location. So so in this particular case, I want to enable this camera, Wi-Fi, and GPS only when the PIR sensor senses a motion. So this is about dynamic power management. Now, coming to whenever we talk about IoT application, one thing we often do is transmit data across the networks. So there are a lot of low energy wireless energy standards. You have the Bluetooth low energy, you have the Zigbee, you have LoRaWAN, you have cellular low power WAN, all this. Now, each of them has its own ranges and its own applications. For example, the Bluetooth low energy has a short range of 10 to 50 meter, and it uses very low power. It can be used with wearables and health devices. So remember that its range is only 10 to 50 meter. Now, coming to Zigbee, Zigbee offers mesh networking, and also its range is up to 300 meter, so slightly much better than the Bluetooth low energy, and it can be used in smart homes and industry settings. Now, LoRaWAN again comes up with a bigger range. You can communicate across 2 to 15 kilometers, and it has a very low data rate, and this can be applicable to agriculture and smart cities. And there is something called cellular low power WAN, which is also going to cover it has a wide area coverage up to 20 kilometers, and it can operate via telecom networks, and it can be used in smart meters and utilities. So we have to choose based on the required range and the power infrastructure that is required, and the data rate at which we want to transmit. So if you look at these features and identify which of these protocols, which of these wireless standards is to be used. Now, coming to adaptive sampling. So, adaptive sampling is again another energy optimization technique where it adjusts the sensing and transmission frequency based on environmental conditions. So, maybe we are going to, let's say we are going to monitor a temperature value. So, when the temperature is very stable, it's not. It is staying at a very constant rate. We don't have to take readings at regular intervals. So, but at some point, if there is some rapid changes happening, then we have to take the readings. So, what typically is done is, we for this duration, whenever there is not much of a change, we are not going to sample much. So we are going to take only very few samples, maybe only very few samples from the maybe I'll take only one sample at this point. And from here on, when the temperature is changing, fluctuating like that, I have to take many samples because the temperature is fluctuating. So when it is a normal temperature, maybe I can say sample every 10 minutes. When there is a sudden fluctuation, I sample at 10 seconds. So this is the idea of adaptive sampling. Now, some case studies in ultra low power IoT. So you might be knowing that a smart soil sensor is going to be placed in a farm, and it can be solar powered, and the data transmission need to be done only once per day, and then it can operate for five plus years. Another ultra low power device is the cardiac pacemaker that you can see here. So most of the cardiac pacemakers comes with very ultra low power, special ultra low power ASICs, okay, application specific integrated chips, and then its life is going to be in the range of 10 years. Now, I mean, to summarize, we have these choices. We have to maximize the battery life, and we have to also reduce memory and CPU usage because of the constraints that we have. And this is going to enable a large scale IoT deployment, and it is going to maintain the lightweight secure. It will have a. We can also have a very lightweight security, and we have to find a balance of all this. Coming to the performance evaluation, since in an energy conservation scenario, we will always apply duty cycling, adaptive sampling, etc. So the latency will be slightly higher. So I mean, still the application will run without any it will run smoothly, but if you compute the latency, since we are not using very high power processor or network protocols, we are going to be the latency is going to be slightly higher. So what about the responsiveness has to be adequate for the particular application. We'll have to have a strong fault tolerance, stability, strong. I mean, we have to have a very high fault tolerance, stability, and scalability. Scalability is going to be excellent because it is going to support millions of ultra low power nodes, and resource efficiency has to be high, and security has to be balanced. So the idea here is we when we operate in a very limited resource with very limited resource constraints, we have to find a balance. We have a balance of different things like latency, power consumption, memory utilization, processor utilization, or the microcontroller utilization, etc. So this is all about the resource constraint system design. Thank you.